If by definition it becomes a single node project, so that's why I'm just trying to build it as close enough to the platform, as scalable as possible. So that's the value that appreciates.
Well, I can just
So that's
everybody hear me okay?
because we all also appreciate.
Anybody not hear me? You wouldn't hear me to answer, would you?
What? Hey. We have a Canadian.
All right, everyone. I think we'll be getting started with our second talk. This one's going to be by Avi. Avi is a software architect here at FC, working remotely from New York, is it?
Yeah.
White Plains, New York. White Plains, New York. Cool. Yeah, so this is going to be about concurrency in large and small. So take it away.
Thank you. Yeah, I'd just like to say this talk is totally half-baked. So you're all like my guinea pigs. I hope that this is worth your time. And if you know, there's anything interesting, then I would love some feedback. If it's not interesting, I think just don't tell me. But I'd love some feedback on if this is working or not working, anything really. But at the end, ideally. I don't really know this audience because I just started a funding circle. I'm based in the East Coast. So if there's anything, if I'm going too fast or too slow, please raise your hand. If there's anything I forget to define, I'm like, oh, just say something, and I'm like, yeah, we all know that. So just please raise your hand, and otherwise we'll just talk about how nonsensical these ideas are at the end. Okay, so I have two theses that I would like to argue for in this talk. The first is that over the past 40 years, there's sort of a paradigm of concurrency that's based on communication that's been ascendant over the past 40 years. But then there's a paradigm of concurrency based on sharing that's been more recently declining, and that these trends will probably continue. My second thesis is that because of recent and ongoing developments, maybe over the next 5 to 50 years, the communication-based concurrency paradigm is going to continue to grow and develop, and may even make it easy and normal to run programs on hundreds or even thousands of computers without even breaking a sweat. Okay, so we're talking about concurrency. This is a Clojure Meetup, so let's talk about CoreAsync for a second. So CoreAsync is a library for Clojure that has, I think, become, maybe the preferred way to do concurrency in the Clojure community, maybe, or at least it's up there at the top. It's pretty prevalent. And if everybody knows what it is, you can all raise your hands and say, let's skip this, but I'll just give a brief overview of it. So in a nutshell, with CoreAsync, you define routines that they run at the same time. And those routines can, fundamentally, they can communicate with each other via channels. So they can send values to each other via channels, receive values via channels. And those channels are basically sequences of immutable values. They're ordered sequences of immutable values. So you have routines, exchange, and they're doing the work, but the way they find out about work they need to do is by kind of reading or consuming these ordered sequences of immutable values, and then they can kind of produce or publish or write more of these values onto these channels, ordered sequences of immutable values. Does that make sense? Anybody? We can elaborate. Okay. So CoreAsync is fantastic. I love it a lot. But I have some pretty upsetting news for those of us who are like Clojure, who have drank the Kool-Aid. It's not actually innovative. So I'm exaggerating a little bit for dramatic effect, but as some of you may know, CoreAsync is basically just an implementation of Go's concurrency model. And Go is a programming system created at Google, first released in 2009.
We get another error from the communicate sequential processes paper.
Yeah, you read my mind. Yeah, so in both Go and core async, the routines are communicating by sending and receiving sequences of mostly or hopefully mostly immutable values. We'll just forget about that mostly part.
Thank you. Appreciate it.
Thanks for the feedback. So, as some of you may know, Go's concurrency model was basically just an implementation of CSP, communicating sequential processes, by Tony Hoare. Is that right? Hoare? Okay, Hoare. Who published this seminal paper in 1978, where he sort of, blew people away by describing and defining this paradigm, this model, this approach to concurrency that was kind of mathematically sound and provably sound. And what's CSP about? Well, I mean, since Go is an implementation of it, and core async is an implementation of it, we've already sort of said, but I want to just reiterate what CSP is fundamentally about in a nutshell. And this is reductive, but bear with me. It's independent concurrent routines that are sending and receiving sequences of values. And we have Crystal. We have other languages and other programming systems that are using the same paradigm. Crystal is a fairly interesting new language. It's about 3.5 years old, so it's still just a toddler, but it's a very promising toddler. And there's Erlang. I've got Erlang floating off in space because I think Erlang is amazing and I respect it a lot. It's really compelling, but I haven't had a lot of success investigating, researching the inspirations and influences on Erlang's concurrency model. But I think it's fairly safe to say that it was at least informed or in some part by CSP. So I've got a dotted line.
Actors.
Right, Erlang uses an actor model, which, some might say it's completely different. What are you even talking about? But I see some similarities.
Actor models come from MIT and back to Carl Hewlett, who's still around, by the way, in the Bay Area, and still publishing these kinds of things, and that is kind of a predecessor to CSP.
Yeah.
Okay, actor models are a predecessor to CSP.
Yeah.
Thank you.
They existed in the early 70s.
Sure about that?
Predecessor. I used to speak with Carl.
That actually jives with what I've read. Actually, it does jive with what I've read. I had a suspicion that was the case from my research. So it did kind of, I wasn't sure about it. It did seem to be my impression from what I saw.
Like guinea pigs.
Yeah, this is great. Keep it going. Keep it coming. Okay, so, well, in the actor model, you focus more on the processes and less on the channels and less on the communication. But still, you have these. If you squint, the actors, you could call them routines, and you can see these routines are communicating with each other and by sending and receiving sequences of values. Maybe sometimes in some cases they're immutable. I believe in Erlang they're mostly immutable. Maybe 100% immutable.
Are you going to put Haskell up there?
I don't know enough about Haskell to include it, but I would love to hear about that later. The biggest difference that I understand is that in Erlang, the routines and in other actor systems, the routines are sending and receiving values directly. They're communicating directly with each other. There's no notion of naming or talking about or thinking about the conveyance between the actors that we might call a channel. So it's like invisible plumbing. And then you have Elixir, which this might be reductive, but it's sort of like an alternate syntax for Erlang, but maybe a really excellent one. Akka is a set of Scala libraries that implements concurrency, also implements concurrency via communication using the actor model. Again, probably reductive. Apparently there's like dozens of libraries that make up Akka, and it's got hundreds of modules and does all sorts of things, but the core of it, I understand it's actors. So we've got a lot of different programming communities, both going back to Erlang and going recently as 3.5 years ago with Crystal, that are embracing concurrency via communication. That's the primary way you do concurrency in these programming systems is with communication between routines or actors and communicating sequences of values. So this is excellent. And I'm really happy about this. And so now I want to take a little detour and talk about the history of concurrency, or a slice of this, a little sliver of the history of concurrency. Very reductive, but so that we can then talk about the future of concurrency, or a possible future of concurrency. So let's do a quick, maybe not so quick, historical review. I'll try. Okay, so like, why do we even do concurrency? What's the motivation? What do we do? Well, it's kind of obvious.
There is more than one computer.
So we do concurrency so we can do more than one thing at a time. But if you take a step back from the way concurrency is usually done in most programming systems, or even, let's say, I mentioned earlier on that the sharing model of concurrency, I see it as more recently in decline, but for a long time it was pretty dominant. And if you take a step back from that and forget about these different paradigms of sharing and communication, so let's say it's 1950 and you're trying to figure out like what the hell, how you can do anything. So there's a bunch of different ways you can do concurrency, right? You could have one program break the work into like a bunch of different files and then have bash feed those files into all these different instances of some other program that you write output files, and some other program is aggregating the results together. Or you could run multiple copies of the same program on multiple computers, split up the inputs upstream and combine the outputs downstream or whatever. And who knows, we're brainstorming, right? But then it's a distributed system and we're fucked. As we know, distributed systems are notoriously difficult to operate, debug, maintain, reason about, etc.
There are also data models where you can't shard your data. And
Right.
this is all saying if you have one gigantic piece of data and you want to have lots of processing work, then you're back to share. It's the only thing that's available.
That makes sense. If you have a data model, the data model
Yeah, I have a
cannot
gigantic
divide
DAG.
up in any way.
Yeah, I have a gigantic DAG. And,
In any way, maybe there is limited ways in which you can divide and conquer. Thank you. Okay, so really, we don't just want to do concurrency. We want concurrency. We want a whole bunch of these desirable properties in our programs that are doing more than one thing at a time. We want it to be predictable, maintainable, reliable, debuggable, operable. That might be a word. Efficient and affordable, etc. And there are others, but there's all these properties we want. And so, it's not just like a blank whiteboard and brainstorming. We have a lot of properties we want, and they all shape our decisions, and they introduce constraints into our decision making. So in order to deliver, I had this hypothesis that in order to deliver these properties in their programs, over time, programmers adopted certain constraints. And they may not even realize they're adopting these constraints. And so I'm sort of like trying to look back and I'm trying to reverse engineer it in a sense. So maybe they didn't realize it, and maybe I'm wrong, but this is just, let's just go with it. Let's see if maybe this works. Without maybe realizing it, they may have adopted certain constraints. One of the most fundamental being the single computer constraint. So for many decades, delivering programs with those desirable properties, it meant doing concurrency as much as possible within the boundaries of a single computer, especially the affordability property. For a long time, computers incredibly expensive. But not just the financial affordability. There are other reasons as well. So, and then there was the single process constraint. Similarly, I think that for many decades, delivering programs with these properties, a lot of it's financial. Memory was incredibly expensive, but you had to do concurrency within the boundaries of a single processor. People, that's what they felt they had to do, is as much as possible do their work within the boundaries of a single process, in a single computer. Okay, bear with me on this. Ryan, this is the bad one. Okay.
You got this.
All right, bear with me. My speaker notes just went down to like 3-point type because there's way too much to fit. So I apologize.
It's too long, don't read it.
Yeah, I know, it is too long, but I don't have any other bridge to my next slides. Let's sum this up. Okay, so for decades, the adoption of these constraints, again, maybe unknowing, unconscious adoption of these constraints in pursuit of those desirable properties, it meant doing as much as possible on a single CPU. And it turns out you can do a lot with a single CPU. You know, so for a long time that was fine. As long as, especially when your bottleneck is I/O, as opposed to computation. And in the era when most computers had a single core, a single CPU with a single core, which was a long time, the best way of increasing the number of simultaneous things a program could do without turning it into a distributed system or stuff like that, crazy stuff, was to scale up. And you could scale up by just waiting a bit. Wait a few months, buy the faster chip, buy the faster memory. You just had to wait a little bit. For a long time, you just had to wait a little bit and buy the next chip, and suddenly your system has great increased throughput. It's like free scaling. Well, not free, but almost free. And for a long time, that helped. And it sort of seemed to work to some degree. And during this era, shared memory approaches to concurrency were kind of the dominant model. And I mean threads, things like threads. And that's even though communication was easier to reason about. Easier to reason about, and it's more likely to lead to delivery of the desirable properties. And I'm sort of taking that as a given. Maybe that's a separate talk. I need to defend that, but I believe that to be the case. So this is just part of my argument that communication-based concurrency is easier to reason about and more likely to lead to delivery of the desirable properties. But despite that, it was viewed as too slow and too costly in terms of performance. You needed extra memory, you needed to be copying values and things like that. And that was because we were trying to get as much work as done as possible to an extreme degree from a single CPU with a small amount of memory. And because beyond that, we'd have to venture into this scary no man's land of distributed systems. And so then it's no coincidence that it was around the time that CPUs stopped getting faster. They stopped scaling up, and they started getting wider. They started scaling out, as Moore's law started petering out. Around that time, communication-based concurrency and immutability both started to become more attractive to people designing and building programming languages, programming systems. It seemed more practical and maybe more necessary when you have these wide systems. One day I'll have slides for all these points. So suddenly, the biggest challenge and the biggest priority was no longer to do as much work as possible with a single core. It was to do as much as possible with 4 cores, or 8, or 16, because that was how you were going to increase the throughput of your program, by taking advantage of the extra width, the scaling out. So computation no longer felt like the bottleneck resource within, and memory didn't feel like the bottleneck resource either. And we had tons of memory by this time. And the single process constraint kind of faded away because we had so much memory, it was so cheap. I've seen so many Python systems with hundreds of processes. So anyway, with the single machine constraint, this drive to avoid making it a distributed system at all costs because it's scary as hell, that remained in place. And to a large degree is still in place. Okay, so that's the story of how we ended up actually adopting the CSP widely. So why did we end up adopting CSP widely, but it took 30 plus years, 31, that's 31 dots, 31 years after its initial publication to really be widely adopted. And so I think that in a nutshell, computers started scaling out. They went from 1 core to a dozen, from multiple dozens. 128K of memory to 128 gigabytes of memory. We shifted from focusing on scaling up, scaling within a single computer, to scaling out and going wide within a single computer. But as I said, the single computer constraint was and is still in place for the most part. But I think that there's something that's been happening over the course of the past 15 years or so that may be starting to relax that constraint as well. Big data. Nobody? I thought this is the Bay Area. You gotta get all excited.
Is that blockchains?
It is not.
Yeah, so
let me try a different motivation here.
Sure.
We didn't have gigabit interfaces between machines until around 2000 or so. And they were very expensive, and 10 giga interfaces didn't appear until mid 2000s.
yeah, that makes a lot of sense.
So not being scared, it's just if you wanted to send your data out, you were going to go across this relatively slow interface. Even gig is slow.
Yeah, that makes a lot of sense. I'm gonna add that in.
And our data closets were smaller than football fields.
Yes. So we didn't have the physical space for all the computers we needed.
Inside a data center?
What was that?
So have you ever been inside a data center?
I'm not sure.
They make Walmarts look
I've
small.
been inside data closets. So in 2004, Google published their MapReduce paper. In 2011, Yahoo released Hadoop. So big data was happening. And you had these large web companies having these ridiculous data sets. And to the point where there was no choice but to create a distributed system to do certain jobs. They had no choice but to go distributed, because otherwise, even with the biggest computer, it would take days to run a certain query or do some certain computation, and it just was untenable. So we have Hadoop, and Hadoop came out in 2011. This is already 5-6 years after I can do math. After MapReduce paper, and Hadoop made it a lot easier for anyone to get started with processing massive data sets using multiple computers, creating a distributed system to process massive data sets. But it was still hard. I have never been able to wrap my head around Hadoop. So it's much easier, but it's still, there's still ways to go. And in 2011, LinkedIn donated Kafka to the Apache Foundation, and Kafka helped make it easier, cheaper, faster, simpler, etc.
Oh yeah.
For programs running on different computers to communicate sequences of immutable values via channels. In 2013, LinkedIn donated Samza to the Apache Foundation, which made it easier, cheaper, faster, etc., to create programs that would read from Kafka channels and write to Kafka channels. And then in 2014, we had this explosion of hosted services and managed services for doing similar things, very similar to the Kafka and Samza models. The conveyance for producing the channels for conveying data between computers and processes, and then the programs that will actually consume and produce that data to and from those channels. Making these kinds of distributed systems even easier, even cheaper, even faster, even simpler. The barrier to entry is much, much lower now in 2014, and they become even easier to use today and more reliable today. 2016, there's a library called Kafka Streams introduced. It's a very excellent library. It runs in the JVM. It's a really, really good library it makes it, again, easier, cheaper, faster, simpler to design and build and deploy and operate fairly sophisticated, scalable, fast, fault-tolerant programs. So there's a lot of features in this library that are pretty solid. Again, programs that read from Kafka channels and write to Kafka channels. So, quick review. We had these constraints in the past. That's weird. Okay, yeah, those constraints at this point today, they're already in the past. We've moved beyond them. But as of today, the single computer constraint, right now, it's still the default assumption for most programs and most programming systems. As much as we love to believe that, the wisdom of the Clojure community is just kind of waking everyone up, it's taken a while. So the single computer constraint is still sort of this default assumption for most programs and most programming systems, this single computer constraint. Distributed systems are still scary, or at least they seem scary. Now you have many of the leading programming systems, frameworks, libraries, and communities are now defaulting to doing concurrency with communication. That's almost becoming the default way. It's becoming prevalent, but still usually within the context of a single computer. That's the context in which they're thinking about it, the way they're doing concurrency. But maybe single computer that constraint is becoming a constraint of the past. Now we have Kafka, we have Kafka Streams, we have Kinesis, we have Lambda. Writing, let's say they're programs. Maybe the definition of a program could change a little bit. But maybe they're programs that do concurrency with communication, but on multiple computers. Maybe 2, maybe 200, maybe 2,000. It's becoming extremely accessible and extremely practical. Every single day, it's getting more accessible and more practical. And so maybe we're on the cusp of seeing this single computer constraint being lifted. And maybe therefore we can start approaching sorry, one paradigm to rule them all. So communicating processes, communicating sequential processes, communicating concurrency via communication as this paradigm you could use everywhere. Maybe you could write a program that uses communicating processes and maybe it runs on a single computer, or maybe it runs on 1,000 computers. Maybe that's just an implementation detail, if you're using the paradigm right. Maybe it's just a runtime configuration setting. And that's what I got. So thank you. And I would love some feedback if this.
Timeline for your TD, semicolon, whatever, might be a way to attack it.
Timeline's a great idea. Thank you. Let me write that down. Yeah. Go ahead, please.
In the last 2 weeks, we've seen Spectre. You should
What was it called?
Spectre, the
Spectre.
CPU speculative extraction.
Yep.
Those might scare people off from running code from different vendors or code that's not meant, it's a security problem. You might want to just, as a matter of data processing, have them communicate over the network just to avoid any security problems. So that could scare people off the single CPU.
Interesting.
I think so. There's a lot of crypto people I'm talking to. Concurrency first. We're talking about that later, yeah.
So you mean speculators, right?
Is your dream of I just write my program and has a bunch of these communicating processes and either I run it on one box or 1,000, doesn't matter. Is the Erlang VM the manifestation of your dream?
I think it might be. So I have a slide on here where the notes in here where I didn't have time to go into this, where it sort of says something like, and then there's Erlang, which sometimes feels like this like alien artifact that just super advanced aliens from the future dropped on us. You know, because again,
The Erlang VM is just like, hey guys, still here.
I don't know if this is true, but I've read that you can take an Erlang program and it doesn't really care if you're running one machine or 100 machines, and it still works the same way. It's the same code. Yes?
I know some people in the Erlang community. There's a distributed Erlang sort of sub-community. It is kind of cool, but from within there, they're definitely, they feel constrained as well. Erlang does failure semantics better than CSP. Like CSP demands that you make a channel just for every error that you're sending, which is a bit overhead. Erlang says, oh, make a processor supervisor tree. And then Elixir makes that easier, but it's still the same thing. And once you do distributed, there's something about like you can't do more than 100 nodes without it being kind of an enormous, some kind of pain. I haven't used it myself. I hear that. So
Okay, so maybe the implementation has some issues.
the VM itself doesn't care. That's the
Right.
that's the main thing. Is they kind of.
But also like the programming language, you know, it's the same program, it's the same code. Maybe the limit is 100, maybe we need to increase the limit, right? But maybe it's still the same program, the same code, but they're running one machine or 50 machines.
Yeah.
And that's still cool. It's
Yeah.
super cool.
It is cool.
Yeah, please.
I was so waiting for you to, I thought you were burying the lead. They're like, oh, but shared memory is coming back. That's kind of like where I was like, oh, really? All right, well, pass the doobie, I'll smoke it.
Was that good for you or bad for you?
Well, I mean, there's a little notes. It's like you're burying the lead. Like if you're gonna say, yeah, shared memory is coming back, I'm like, all right, cool, let's hear about caching. You know, but that's kind of where I thought we were going.
Were you disappointed or were you not disappointed at the end?
You know, let's keep this all, you know, like we all love all types of things.
Yeah, also, why don't we like take one or two more hands and then we'll break, and then I'd love to hear some feedback more individually rather than making everyone stay in their seats, so please.
I have a question. On the theme of going to a single computer and talking about Back to the Future, did you look at Go Author's previous work?
I noticed that it exists. I became aware of its existence, and there is a language.
Well, before that, there's a distributed system.
Oh.
Blend 9.
Yeah, there's a programming language associated with it.
Oh, that's true. But you were talking about lifting the single computer restraint.
Cool. I'll look more closely at it.
You can't use it. It's not. Well, you can use it. It's not. You can't use it. You can use it by yourself.
Well, it still is a work of prior art. It's still going to be interesting and informative.
Oh yeah, no. I mean, just the topic of the history and the whole theme of Back to the Future.
Yeah, I really want to try to make these connections and bring more consciousness of the past forward to the present, and
Go is just the language side of things, but the previous work is more the whole operating system.
Cool. Yes.
Back in approximately 2011 with this group, which was started by Ahmed Rathmore, he gave lectures on Ring, which has allowed multiple computers to all talk to each other using the Ring software, or Rabbit and other things. So this has been around with this group since around then.
I mean, ways of communicating to machines, like
Yeah,
having...
for using Clojure with that was one of the very earliest examples.
This, you said Ring, but you don't mean the web library. You do mean the web library. Okay.
The routing.
Okay. Cool. Thank you. Maybe, do you mind if we break and we can just talk individually? I just feel like we should let people go, this is enough. So, thank you so much for your attention, I really appreciate it. Just